Namaste dosto. Imagine you are picking sweets from two different jars, one after the other. The chance of picking your favorite sweet from the second jar depends on what you picked from the first jar. This is where the multiplication rule of probability shines. Let's say we have two events, E and F, happening in sequence. When the probability of the second event depends on the first, we apply the multiplication theorem. The formula reads, P of E intersection F equals P of E multiplied by P of F given E. In words, the probability that both E and then F happen is the probability that E happens times the probability that F happens assuming E has already occurred. Alternatively, if you prefer, you can switch the order. P of E intersection F equals P of F times P of E given F, provided the probability of F is greater than 0. This rule helps when events influence each other, like drawing cards one after another or conducting sequential experiments. Think of a two-stage probability tree branching with conditional chances at each step. That's the visual that really brings this to life. So, next time you see one event affecting another, remember, multiplication theorem is your best friend. Moving ahead, let's formalize this rule. Suppose E and F are two events, and the probability of E is greater than 0. Then, the probability that both E and F happen together is given by this key formula. P of E intersection F equals P of E times P of F given E. Mathematically, P of E intersection F is P of E multiplied by P of F given E symmetrically. If the probability of F is greater than 0, we can invert the roles to get P of E intersection F equals P of F times P of E given F. This theorem holds true whether the events are dependent or independent, as long as the conditional probability is defined. It is derived directly from the definition of conditional probability, which states P of F given E equals P of E intersection F divided by P of E. Now, what happens if E and F are independent? That means the occurrence of one doesn't affect the chance of the other. In that case, the conditional probability P of F given E simply equals P of F itself. So, the multiplication theorem simplifies beautifully to P of E intersection F equals P of E times P of F. Keep in mind, this simplification holds only if E and F truly are independent, meaning no influence between them. Before applying this shortcut to a problem, always verify independence carefully. For instance, tossing two separate coins fits this rule. The result of the first toss does not change the probability of the second. Picture this with a Venn diagram showing separate, non-overlapping events to highlight independence. Very simple and neat. Chalo beta, time for a practical example. We have a standard deck of 52 cards. What's the probability of drawing two kings in a row without putting the first card back? We denote the first event E as picking a king on the first draw, and the second event F as picking a king on the second draw after removing the first. Applying our multiplication formula, P of E intersection F equals P of E times P of F given E. Step 1. Probability of E, selecting a king first, is 4 kings out of 52 cards. So, 4 divided by 52, which simplifies to 1 over 13. Step 2. After removing one king, only 3 kings remain and 51 cards are left. So, P of F given E is 3 divided by 51. Multiplying these, we get 1 over 13 times 3 over 51, resulting in 3 over 663, which simplifies to 1 over 221. Thus, the chance of drawing two kings in succession without replacement is exactly 1 divided by 221. Shabash. That's how the multiplication theorem helps in realistic scenarios. Next, imagine a bag problem where we transfer balls between bags before drawing. Suppose bag 1 contains balls of different colors. We pick one ball from bag 1 and transfer it to bag 2. Then, we draw a ball from bag 2. We want to find the probability that the final ball drawn from bag 2 is white. This problem involves dependency because the composition of bag 2 changes based on which ball we transfer. To solve this, we apply the law of total probability combined with the multiplication theorem. We consider all possible events, each ball that could have been transferred from bag 1, with their probabilities P of E sub I. For each, we multiply by the conditional probability P of drawing a white ball given that transfer, P of a given E sub I. By adding these products over all possible balls transferred, we get the total probability of drawing a white ball from bag 2. Visualize this with a tree diagram. Branches showing each ball transfer option, and subsequent branches for white or non-white draws. This systematic breakdown captures dependency beautifully. Here's a neat algebraic application using set intersections. Suppose P of E equals 0.4, P of F equals 0.5, and the probability of union P of E union F is 0.7. We want to find the probability of both events happening together, that is, P of E intersection F using the formula for the union. P of E union F equals P of E plus P of F minus P of E intersection F. Substituting the values, 0.7 equals 0.4 plus 0.5 minus P of E intersection F. This means P of E intersection F equals 0.4 plus 0.5 minus 0.7, which sums up to 0.2. Therefore, the probability that both events E and F occur together is 0.2. If P of E is greater than 0, we can compute the conditional probability P of F given E as P of E intersection F divided by P of E, that is 0.2 divided by 0.4, resulting in 0.5. To wrap up, let's recap the multiplication theorem's main formulas. First, P of E intersection F equals P of E multiplied by P of F given E. Second, by symmetry, P of E intersection F equals P of F times P of E given F. Third, for independent events, P of E intersection F equals P of E times P of F. Remember, this theorem links joint probability with conditional probability and marginal events. It's especially useful in multi-stage processes where the outcome of the first event affects the next. The key is to identify whether events are dependent or independent before choosing the correct formula. Common applications include card drawing, ball selection, conditional trials, and sequential sampling in real life and exams. Arey wah! With this solid understanding, you are well equipped to tackle probability questions involving event dependencies. Thank you for your focus today. Now, quick checkpoint. Imagine selecting a red ball and then a white ball without replacement from a bag containing multiple colors. Which form of multiplication theorem would you apply here? Think about it. Keep practicing this theorem, and soon, solving complex probability problems will feel like a breeze. Shabash, and all the best.